12, you just put the 10, 12 is cleaner. I think this is the first thing to do.
But just to add what Sheila said, so you make, if you put a 6, 12, it's clear that you have weaker for the second labor, but still strong enough. You want it to die. The 10, 12 die. If you want to replace that by a Gaussian, fine. This is just a question of convenience. What you want is an attractive potential just between nearest neighbors. And then when you go to the second nearest neighbor, it dies out. The particular shape at this level of model makes no difference.
Yeah.
Once you go to more detailed models, then the shape makes a difference. Here is qualitatively, your resolution has to do with this bit-bit separation. So what I want to make sure it's not that just it's weaker. You want to make sure it dies when it goes to the next nearest neighbor.
Okay. But to be completely honest, the reason we picked, when we started, we picked the 10-12 or the 6-12 is because of the number. And it was the first thing to do. But now in my group we have arc, amber, and modified. And we use Gaussians, we use fourth power, we are exploring a different range of stuff. But this is just, I'm talking in general. What are the ideas, what are the principles in developing a coordinate model, why I want to do it. So let me repeat a little bit to continue from José's talk. In doing something like this, you have to have a question in mind, because there is no perfect model that answers all the questions. And I hope I made this clear with the idea of the multiple resolutions. So you want to have a particular physical question in mind that you can address, and then you can define the model, the best model to address this particular question. As an example, when I was working with José, we wanted to disentangle energetic and entropic factors in shaping the four-dimensional energy landscape. And José already told you about what's important to get the four-dimensional energy landscape. I can get thermodynamics and kinetics from it. So the free energy, as all of you know, is an enthalpic contribution and an entropic contribution. And both of them are important in a protein because proteins work at room temperature, so this T is quite large. And one can associate energetic contribution clearly that the different energetic interactions between the different residues. And if you think about the coordinate level, is the attraction between these effective beams. What is left, particularly the entropy, you want to be accurate, if you want to put the water into it, there is also the entropy of the water, but in a coordinate model, this entropy is just a conformational entropy. So, if one wants to, at least at the zero-order approximation, understand, disentangle the energy effect and the entropy effect in shaping the free energy landscape of a protein, the coordinate model can do a very good job. And I'm going to show you one. So, as I said, you can think that what you want to look at shaping the landscape are this heterogeneity, the deviations from the perfect funnel. And there are two sources for this. In the energetic part, there is the fact that different amino acids interact in themselves with different strength, but they can attract or repel each other, and there are different sources of interactions. So for instance, you can think that this is your simplified protein, you can think that, and I'm coloring the beads according to the amino acid type, you can think that red and red attract each other much more strongly than red and green. So this contact would be favored energetically with respect to this one. This would be an energetically favored configuration. But in order to make this contact, there is a large entropic price to pay because there is the configurational entropy, this loop entropy here, that is reduced, while making this contact, the entropic price is much more. So the entropy goes in the opposite direction. So there are two sources of heterogeneity, two sources of frustration, if you want, and this is why people talk about energetic and topological frustration. Topological frustration being this entropic heterogeneity. And this can be quantified more rigorously theoretically. So, and the idea that we had when we started to automate with Z was that if the protein needs to fold to a particular shape for functional reasons, or maybe if the shape is given, we can think that evolution produced as much as possible the heterogeneity in the energy part, and what is left is the heterogeneity in the entropy part that is just there because of polymer physics. And you cannot do anything about it. If this loop is long and this loop is short, I think short and long, we engineer the sequence as much as we want. So this is what we did. This is what Jose described. This is what we did in 2000. And we was clear that, so in order to prove that, you can design a model, a simplified model, where the energy is the same for all the interactions, and see if you can reproduce something that is close to reality. And if you can do that, it's the proof that this idea is correct. And this is what we did. So another way to see this problem is the idea of energetic and entropic contribution. Is if you, I'm going to make a very cheesy analogy, sorry. You can think about folding a protein as solving a puzzle, in the sense that you start from a very disordered state and you want to go down to a very ordered, compact state. And you can think about two strategies to solve the puzzle. One would be, you can be guided by color. You want to match pieces. If you have, for instance, the design, if you know that you are going to reproduce a certain design, you can assign a certain score if you match pieces that will produce the design, and you can think about this as energetic matching. While another strategy would be to look just at the geometric complementarity of different pieces without caring about the design you want to reproduce it there. And then that you can think about this as the entropic contribution. So if you have to solve a puzzle like this, geometry is not going to help you much. So this would be the analogy of the protein, would be the folding mechanism completely dominated by energetic effects. If you have to solve a puzzle like this, here the color matching doesn't help you much, and that would be a folding mechanism completely dominated by entropic effects. The only thing that matters are geometry complementarity. What about real proteins? Well, we expect real proteins to be in between, but this is a good way of thinking about the problem, because if one can prove that this is the dominant part, that even if it's in between is a little bit tilted to this side, one can use this approach as a zero-order approximation and then try to use perturbation theory or any correction you can get to move to reality. And this is what, as I said, this is what we did with this. And this is what, now many people, this is the paper where we proposed this, and this is what also Jose referred to as structure-based model, where you only care about the geometric details. You try to reproduce geometric details, encoding them into bond, angle, and the inner potentials, and then the energetic part is trivial. It's just smooth and orchestrated and completely homogeneous. And this is, for many systems, this seems to be a good starting point. One thing, so when I started as an assistant professor at Rice, one question I was interested in is how all of this scale with the size of the system, because us and many others have proved that this approach is pretty good for small protein. It's true that for small protein, the entropic effects are dominating the shaping of the energy landscape. What about larger protein? And one can think about two things. Going larger and larger, the dominant effect becomes more and more dominant, so that will be good news. And you can use the same approach even with more confidence. Or, going larger and larger, there is more room for fluctuations. You can accumulate heterogeneity in particular spots, and that can cause deviations from what you expect from small molecules. Different effects can come in. And I would say, after working several years on this, I would say that both scenarios can happen, and one has to be careful on the model and on picking a model depending on which one is the case. For instance, and I hope I'll get to telling you something about one particular study that we're doing now, and Jose also mentioned this, in many proteins, this route may be preferred because you can engineer function like this. You can have different, you can play with the competition between entropic and energetic curves to have switches and functional properties. For other proteins, this may be the preferred route. So one of the systems we started to test this was supposed to be the first step in a much larger project, but the student graduated in between, so I hope one of the new students is going to work on this. This is, when I arrived in Rice, I was contacted, in the very beginning, I was contacted by Kathy Matthews, she described to me the system she's been working on for a long time. This is the lactose repressing protein that is one of the premier systems for studying gene regulation. And given the fact that Kathy Matthews is also the dean of my school, I didn't even have a choice, so I studied. Fortunately, I'm very interested in this system, so was very good. So this system is very large. It's a multi-domain system. It's a tetramer in vivo. But it can work also as a dimer, so there's already this question of why you want to make a tetramer if the dimer seems already to be functional. And there is allosteric motion. There are these two domains that are connected by a double hinge region. There are two passes, or three passes, or back and forth between the three domains. So the architecture is not trivial. There is a dentamization domain that is completely unfolded when we don't have the tetramer, and there is a DNA binding domain that is completely unstructured in the absence of DNA. So how does the energy landscape, the energy landscape of this protein affect the function? How can we go from the energy landscape of the monomer to the one of the dimer, the one of the tetramer? This, as I said, is a work in progress. I'm going just to tell you about the energy landscape of the monomer. So what we did, we used the same structure-based approach, and we got a quite complicated energy landscape. So these are two sets of reaction coordinates. This Q, you already heard from Jose, is the fraction of contact in a particular stage in a particular structure that are in common with the native structure. So one would be the crystal structure, because there are fluctuations. This is the closest we can go, because there are thermal fluctuations. This is the closest we can go, but it's pretty close to 1, and so this is the native state. 0 is the completely unfolded structure. This is the unfolded state, the unfolded minimum. Different contours are show a difference in 1 kT of the energy. And but there are other things in between. In order to get these other things, we need to use another coordinate, and this coordinate is what we call, it's not that trivial to define another coordinate for this, and I'll talk about reaction coordinate tomorrow. This coordinate is what we call the partial contact order. Is in order to get some additional information about the collection of structure during the folding mechanism, during the folding, thinking that Q simply tell you something about the fraction of the protein that is folded without saying where. The extra information we'd like to know is which part of the protein is folded and which not in an average way. So we define this what we call PCO, partial contact order, that is the sum and I'm going to explain what it is. So if I define Qij per pair of residues, Q Q is equal to 1 if the contact is formed, if residues I and J are in contact, and the contact meaning they are within a certain threshold. There are, remember I'm using a potential like this, so I can say if this is the distance R, and this is the potential Vij, if the two residues, this is Rij, are within a certain cutoff distance, I consider this interaction successful, and I discretize this in the function Q, that is either 0 or 1 if the contact is formed or not. And I can wait, so if I just take this Q, is the Q parameter, and then I normalize it to 1, is the Q parameter here. I can weigh this Q with this weight L, and L being the loop length, so the separation along the sequence between residue I and J. So if I have I and J here, not only I look if I and J are in contact, but if they are in contact, I don't count 1, but I count how many residues I have in between. And this way I can take into account, well, there are theoretical reasons for doing this, because it's related with the measure of entropy. So this is additional information. And clearly, if you have a small value of this parameter, means that mostly you form local structure. If you have a large value, it means that you form, you bring together parts of the protein that are far apart from. Yes?
Excuse me, Qij, does it depend on R or it's just binary 0, 1?
Is binary 0, 1. Depends on this. I mean, you can define a Qij map for each pair. This is a function of the structure I'm looking at. Okay. So what we do, we collect a lot of simulations. I'm going to tell you in a minute how to get this free energy from the simulations, and then we plot this as a function of these two coordinates, and we look at the structure, the features of this mass. So as I said, there is clearly we can identify this minimum here is the unfolded minimum, and each point is a collection of many structures, it's an ensemble. So if I take all the structures in this minimum A, and I look at this ensemble, I take the average over the ensemble, and it's represented here with the color scale given here, with probability of forming particular contact on the structure, average over all the structure in this ensemble here. And this is a representative structure. So PCO, the partial contact order is quite low, and clearly only local secondary structures are formed. And then you see with the probability that they can form and break, nothing is completely formed. But if there is something that starts to form with local ellipses. Then there is this minimum here that is an intermediate, but also there is this large deviation here. And we are really puzzled by this. There is clearly this protein, rather than going through the correct folding pathway, can take an excursion in a direction that is not productive. And we want to look at what's going on here, so we take a sample of this ensemble, and we do the same thing, we average over all the structure of the ensemble, and this is what we get. You get that there are parts of the proteins that are far apart along the sequence, basically the beginning and end, then try to form contact, try to make contact. And this part here, we did some perturbation theory, this deviation gets stronger and stronger if you put some non-negative perturbation. So this is a non-productive route that can be populated nevertheless, even if there is no energetic fluctuation. And if you put some energetic fluctuation, populate it even more. But eventually, the protein does find the correct folding route, and this intermediate is always populated. It's a productive intermediate. And this is depicted here. Again, we take the average of this ensemble, and there is a probability very high in this region to form basically 1, and it corresponds to this part of the protein here. One domain is completely formed. The other domain is very floppy and only secondary structure. And but after information on the domain, everything goes quite well, and from here you go to the folder of the same such. So the experimental, as I said, Kathy Matthew asked me to do this, and when we got these results, she was very, very happy, and we spent 3 years to try to purify the protein to...
That's another non-predictive
Yes.
association?
Yes. This is an alternative folding route that is populated like only 1% of the time. We have in mind, this is something that we still want to do, to try to engineer mutations so that we can switch to this other fold. This is extremely slow folding because you require, if you go to this X here, you will fold this other domain first rather than this. It is extremely slow because of the connectivity of the two domains. And but 100% of the time you find it served. In experiment you cannot detect it. But we were thinking that maybe we can engineer a way to do it.
Have you looked at, so I was fascinated by these folding trajectories that we saw the other day. And I was wondering if you've looked at trajectories as to how these things fold in terms of this energy balance.
Yeah, I'm going to.
Oh, you do.
But this alternating folding routes, that's a good question, because on proteins like interleukin 1 beta,
You can switch from one to the
you
other.
can switch from one to the other. And for functional reasons, when you want one function, you may want to have something that is in the middle of one route, and then you go to the other one.
Yeah, so some
1%
flexibility
looks like a very small number, but it's a measurable number. So you can
Yeah.
actually use minor, it's a few KTs here or there. You can make 1% become 30% very fast.
Yeah,
It's
yeah.
actually very good.
So hopefully in the near future. So when we got this result quite fast, but it took us a long time to, because as I told you, the experimental lab was studying the protein, the tetramer protein. So we had, in order to test these before we proceed with the dimer and the tetramer, we wanted to make experiments on the monomer. It was not that easy to purify the monomer. It took 3 years, but eventually we did it. I asked my student to also go into the lab and get involved with experiments, and then I got a call saying, can you please get the student out of the lab? Which apparently she was breaking out. But, so eventually we did the experiment, and this is Fire, the student who did all the...
What we call the lab.
She's not IBM. So this is what came out of the experiment. There was a burst phase, so they did experiments, they did stock flow, and they did CD, stock flow CD, and CD, and fluorescent injection.
So why don't tell people what burst phase is? So everybody knows what burst phase is?
It's an extremely fast.
Burst phase is whatever the experimentalist cannot measure.
Yeah.
Basically, the experiment has a time limit, and basically when you can measure, there's a window, and already something happened.
Yeah,
You start with
exactly.
a folding protein, you put some folding
An extremely fast event that you cannot detect in the resolution of the experiment. But clearly, so if you start to put some denatural, you can start to see what's going on in this burst phase, and both the CD and the fluorescent kinetics could not be fit by single exponential.
But it's interesting, but it's important for you guys to highlight. But sometimes, because you can't measure, doesn't mean the important thing is not there.
No.
So when you observe that, you will observe some things already taking place. So it's always it's
Yeah.
good always to keep an eye there.
Let me show what we get combining the two things, because it's interesting. So this is what the experimentalist proposed. And so there is this time scale, there is something that happens that seems to speed up with the natural concentration. So this is an indication of a non-productive direction of folding, because it becomes less and less important as you demonstrate the protein. And then this is the clear Sherman plot from the other coefficients, the folding and refolding and unfolding overlap. And so this is what they propose, that there is this equilibration, there is some non-productive stuff going on that has to equilibrate with unfolded state at the beginning, and then eventually the intermediate state is populated by the reactive state. And this is completely equivalent to our folding answer. Yes?
Did I know your results in the experiment?
No. Because in the meantime, another professor already tried, Pernilla, and she was the one, Pernilla Wittgenstein, and she was the one in charge of the experiment, but we didn't show them our results. So this is what they came up with. And so, but I wanted to get a more quantitative agreement. So you can open any biochemistry book and find differential equations for the kinetics of a mechanism like this. And if you solve, so if you consider that there is a time scale to go from here to here, and a time scale to go from here to here, and a time scale to go from here to here, you can put all of these mathematical terms, as we've seen already yesterday in Daniel's lecture. And you can solve these differential equations, and this is what you get. If you assume that the initial, with the given initial condition, the initial condition would be that at the beginning, you start the experiment, everything is unfolded, the population of the unfolded state is 1 at time 0. This is the solution at the time t. And with this different table. And then you can consider the fact that your signal, whatever it is going to be a function of these populations with the coefficient A and B. It is the amount of signal that is intrinsic to the whatever is going on in this bar space. And that this coefficient B, that is the amount of signal corresponding to the intermediate state. And then the negative state, just assume that you have your full signal, because you normalize between 0 and 1. And we can make a very simple theoretical estimate of both the CD signal and the fluorescent signal. The CD signal is just what we look at. The CD signal is normalized between 0 and 1 and looks at the amount of secondary, particular amount of alpha helices. So the corresponding theoretical signal would be just, the most simple thing you can imagine. We identify the alpha helices and we take the average, so what we call the helicity and function of time. We do the sum over all the helices for all the residues belonging to all the helices of the angle, the dihedral angle corresponding to this residue I times t minus the dihedral angle of the perfect helix, that would be 60 degrees, and is what we find in the genetic structure, square average. This is the normalized signal, and you can normalize it, yeah. And this is, it goes in the same direction with the CD, and you can imagine that this is the theoretical equivalent of a CD measurement as a function of time. If you look at the particular frequencies indicating the helix signal. Similarly, the fluorescence intensity, this is a tryptophan fluorescence. There are 2 tryptophan in this protein. Position, so there is a tryptophan at position 201, and this protein is about 350 residue, and at position 220. So what we can do, because the fluorescence is quenched as the tryptophan starts to become bored, again, the most simple thing one can do theoretically is to try to monitor the kinetics of the signal, is to take, to define the Q fluorescent, or Q tryptophan, that would be the same as Q, but as a function of time, and computed and restricted to the Q tryptophan. So that would be the sum over all the contacts, Ij, restricted to the fact that one of them has to be either position to 1, or tryptophan to 1, or tryptophan to 20, of Qij as a function of time. So these are 2 simple assumptions that allows us to monitor the same thing theoretically. And then we can try, because the reason for this is that we need to find a way to quantitatively validate this landscape, and we need to find something that is robust against the assumptions we make. We know for sure that, as Jose already mentioned this, that the relative position, the relative barrel height is something that is extremely sensitive to energetic perturbation. So this would be not a good quantity to compare between them. Am I late? How much time do I have?
You have until 12:05. I don't know where you start. Start 5 minutes late?
Okay. Do I have to stop for questions? I can stop right after this and then continue.
Yes, you can hold your basically 10 minutes. You can take another 10 minutes and then you type the question.
Okay. So, yeah, so, and also we cannot compare dependence on the dimensional because we don't have dimensionals in the simulation. We have temperature, and as I mentioned, it's not exactly the same thing. So one thing, a good thing to compare was the change in the two signals, because the two signals measure, one is the formation of secondary structure, and the other one is the formation of structure around the tryptophan. So we want to see how these two things come together, and this is really indicating the folding mechanism, what's going to be formed first and going to be formed later in quantitative terms. So this is what we did. We solved this equation, we used this definition, and this is the final result. So what I'm plotting here is the Q signal as a function of time, both for the theoretical and experimental data. So we took the experimental data, and experimental data are these two colors here, this kind of brownish and pinkish color. So this is, and I color them differently according to the time scale they refer to. So the experiments start here because this is the dead time of the experiment, but the simulation is at the simulation data. In simulation, everything is in the computer, so we can look at the whole thing. So we see that there is a jump in the CD from unfolding to this bar thing, this bar phase, in the dead time of the experiment. And 40% of the secondary structures form, and this is what can cause troubles with the incorrect packing. But then, and this is what is resolved in this time scale T1, and this is when the experiment starts to detect something, that is the transformation of basically the depopulation of this region here and the movement of the protein toward this part here. And then there is the intermediate, and then it goes. So, and as you see, not only the experiment and the simulation overlap very well, but we can use the simulation to extend the prediction, to extend the experiment. We have overlap from here on, and we can use the simulation to understand what's going on before, to interpret the CD of fluorescent data. And all of these, I mean, we did a lot of tests, perturbations, so all of this is very robust. And these two papers, so we published two KMS papers back to back, and we got a lot of press because apparently people like this picture. So I think I can stop here and I can continue. So this is just to give you an idea what kind of questions one can try to address with extremely simple model. What I would like to do this afternoon and then tomorrow is to tell you how to move from what I've told you is just a zero-order approximation. If one wants to push and make refined prediction, how one can go and make more refined models. But let's stop here.
Question back there.
I'm very fascinated by the work you did, and I had a couple of questions actually. So first one, this protein simulations you did, is it? So you did it using only, you assumed only carbon atoms again, right? And are you doing simulation of the all polymer, all protein at the same time, or you split it as on the previous slide and the boxes and you run on each box separately?
So one protein at a time, but you need to do statistics. So you do multiple folding and refolding and unfolding trajectories. The beauty of these models is that they are so simple and so fast to simulate that in a couple of hours you have 50 refolding events for one single simulation. You can watch the protein going back and forth
Does
folding
it
and
depend on
unfolding
temperature or just in time?
in time. I mean, 3 hours of computer time.
Yeah. But it's all protein. You don't split it in boxes and do
One
it.
protein.
It's
You look at one
yes.
protein, and then to compare with the bulk experiments, you create an ensemble,
Yeah.
so you do the simulation many, many times. And you can do a different temperature, and then you have, let's see, I'm sure I have, not just one. So if you combine together the simulations of different temperatures, you can use statistical mechanics trick
Okay.
to get the best partition function and the energy for the partition function.
And can you come back to the previous slide, please? I have another question.
When the computer is responding.
So,
I have the bar. It's fine. Which slide?
previous.
Okay, ask me the question and then respond to the computer.
Oh, okay.
It's not respond, it's all.
Yeah, we have another question here. He doesn't need to go to the other
Okay.
slide.
Could you give more details on the simulation process?
Okay.
How do you evolve the system through time?
Oh, it's integrating the Newton's equation of motion, F equals 1A. And okay, you can use different algorithmic tricks, but it's simply the second law dynamics, because everything is classic. And as I said, it's constant temperature. So you couple you want to simulate the canonical ensemble. So if you just do the integration of the second law of motion for an isolated system would be the microcanonical ensemble. And because these are finite systems, they make a different microcanonical canonical. So you really want the canonical. And in order to do that, you can effectively couple your protein with a thermal bath that is absorbing or releasing energy to maintain a fixed temperature. And you can do this, you can fix the temperature of the bath, and you can do it at several different temperatures, and you can run multiple simulations at multiple different temperatures. And what you have is that, in principle, if you have the Boltzmann distribution, if you really go to equilibrium at infinite time, if you have the perfect ensemble, the probability of observing a given Q, or I mean, you can have a set of coordinates here, and a given energy is equal to or proportional to the density of state, which is Q and E, times exponential the Boltzmann factor. And you can change the temperature. The beauty here is, the nice thing here is that the density of state in principle does not depend on the temperature. So you can do this at multiple temperatures and extract the density of state at multiple temperatures and then combine it in a smart way so that you minimize the error. And the error is going to be proportional to the length of the simulation or something like that. And so this simple statistical mechanics tricks allow you to get omega. When you get omega, you have all those thermodynamics because you can compute the partition function, so you can get the energy. And here is the assumption that you can define an ensemble picture. So when I write this, means that Q is the relevant coordinate, is the slow parameter, because all the other degrees of freedom equilibrate very fast for a given Q. So I can effectively define an ensemble, and Q is a good reaction coordinate. But I'm going to talk about reaction coordinate more. Yes?
Where is that figure?
Okay. So you
And
want
it's
to...
11 degrees Celsius used to learn the...
So you had a question about the previous slide? This one?
Yes.
I wanted to ask what is this on these diagrams, these gray triangle diagrams?
Okay. Oh, sorry.
What is
Yeah.
it?
This is a contact map. So each point, each of these colored points is one contact. You have to read. So from, let's see, for instance, let's say this one is this dot here is the interaction between residue number 40 and residue number some. What is that?
So it's a structural protein.
Yeah. So each point is one particular interaction. And the color is different according to the probability of having that contact form. So this tells, because this is an average over all the structure of the given ensemble. So what this tells you is that you have a very low probability of forming any part of the structure in this ensemble, and mostly is mostly is in the secondary structure around the diagonal. Around the diagonal you have interaction between I and I plus 4, so at
That's
least.
for the unfolding base. Right?
And this is the unfolding basin. While, for instance, if you look at this one, there is one part of the protein, all these contacts here, that corresponds, so the same information is reported on the structure here. All these contacts here form a probability close to 1. So in most of the structures that are found in ensemble, these contacts are formed. While the remaining is formed with something that is less than 50%. Okay.
And the last thing, sorry. So in your energy functional, right? Do you use the same constants for all carbon atoms, or
Yes.
dependently on
Yeah. So this is the assumption we made at the beginning, because we want to disentangle energetic and entropic heterogeneity. This is the simplest thing you can do. You just say energetic is trivial. I let the entropy decide.
Okay.
But later on, you're going to change
Yes.
that.
Okay, I'm just trying to wrap my mind around this experimentals.
Okay.
Okay, so you use your carbon-based model, right? And in this particular case, you're using it with a known protein that you were able to do experimental. So my question is, can you give me an idea of how long that carbon alpha chain that you used, and did you also vary the number of carbon before you even got to the stage of comparing with experimental? So like, for example, if you had a protein that only had like 3 carbon alpha along the entire chain compared to like 15, that's my question.
So I keep only 1 carbon per residue. So given the protein, I fix the number of carbon. So this protein is 350 residues. No, that, yeah. So this kind of approach works usually very well with smaller proteins. And this is what José talked about the last day. For larger proteins, as I said, this case works very well. For other cases, may not, because the energetic heterogeneity may get built in the larger and larger system and have a functional role. But, so I think I don't have an answer in general right now.
Yeah, Cecilia?
Yes.
Yeah, well, I think I'm learning something. But, so your model is based on, your simulation is based on the structure. So did you use the structure of the monomer, or I think there is only the structure of the dimer, right? Or there is...
No, there is the structure of the dimer and the tetramer, so this is what they did. We engineered the monomer and we made sure that the structure of the monomer is consistent.
Oh, there was a... the structure of the monomer was similar?
Yeah, we made sure with CD, with all the possible experimental, without doing the crystal.
But the atomic coordinates are from the dimer, right?
Yeah, but we had to make mutations because the protein didn't want to stay in the monomer form.
No, because that's, I think this protein, because Kat Roy was when joined Gregory Webber's lab, she was working with this, and I think the dimer associates to a fold of the monomer, so it's a particular case, but...
It's a transcription factor, right?
Yeah.
So it's active as a dimer, and the monomer form is not too stable because then they won't get digested.
Yeah, the problem is that to purify the monomer was a nightmare. I was really glad that it was experimental.
See, Jerson, even with your teeth sometimes, put it on the real biology, you don't know how deep's the trouble ahead of you.
used a coarse grain model, and your model matches very well with the experiment. And for the folding unfolding, can you say the sidechain flexibility or the sidechain interaction is not much important here, but for the function like binding, it's very important.
Yeah.
Can you comment on that?
Yeah, I'm going to talk about that more this afternoon. And yeah, so there are several things you can do. You can, first of all, you can check this statement. And I think was the last work I did with Jose before I started my lab. We built a similarly unfrustrated model but with a sidechain. And then you can separate the fact of the sidechain flexibility from the backbone flexibility, and you can quantify and see what's more important. In that particular case, we did it for protein L and protein G. I can show you some results this afternoon. It didn't really matter. Just the packing, or just an average, was average around. But another thing you can do, you can use, and this is also something I'm going to talk about this afternoon, you can use this kind of simplified model as the first approximation, and then increase the resolution later on, and zoom in a part of the landscape you're interested in, and then introduce good balance between different parts.
Okay, so just before we finish, the sidechain is always important.
Yeah.
But when you do a simplified model, you are cheating them on the fact that you're just using native context as being attractive. Right? The question is, when you have to unbalance them, that's when it becomes a scheme. Now, as the teacher already said, when was advertised that she just did this first lecture on this very simplified C alpha model. So it's not a carbon base, in a sense, it's more like saying, I have one bead per amino acid. The fact you put on the position of the alpha carbon is a convenience. Yeah. And now you can go to 2 or 3 beads per amino acid and complicate, and that's what she's going to do as she goes on. So you're going to see, like, there are some problems you cannot do with this simple model. I think we're going to have a few of them. So let's take Chichiro one more time. Before we finish, just have a couple announcements. Remember this afternoon to pick up the directions for tonight at 7:30. And also there is a certificate of participation. So when we stop there after lunch or even now to pick up your map where to go tonight, make sure you get your certificate there. Okay? Thank you. 1:30 sharp. We have Alex. Let's go. You're better.
So there will be a sharp transition in my couple of talks from molecular level to what is fashionably called these days systems level. So I'll tell you about molecular machines, which contain tens of different types of proteins. The whole number of molecules involved is thousands, sometimes tens of thousands. And you'll see that those machines perform huge varieties of tasks. They perform it really fast, very accurate, incredibly accurate, and with a lot of noise involved. And the main thing is, if you thought that what you heard before about single molecules is complex, the level of complexity of the machines is orders of magnitude greater. So for that reason, actually the quantitative studies of those machines are in its infancy. Just basically in the last few years, when works of any quality started being produced, and still lots of work has kind of dubious values. I'll tell you what I mean. What is very fascinating and exciting in this area is that physicists can help a lot, but in order to help in the process of biological discoveries, one has to ask biological questions, not the questions that are leading to creation of elegant, simple models, but the questions that biologists would like an answer on. And the problem with that is that all these biological machines are incredibly messy. So the traditional theoretical physics, it's a good idea to compare it to like a diamond. It's a perfect crystal. You have to think very hard to uncover its structure, but it's doable. You, in principle, can understand everything about the diamond, and you can describe it in a few pages. My favorite comparison is the difference between traditional theoretical physics and biology and real biological physics of these complex machines is like between diamond and miso soup or any kind of soup. So it's boiling, it has lots of ingredients, it's basically a god-awful mess. And only way to succeed for physicists in studies of this system is to embrace this mess, not to try to step aside and find some simplicity, but actually figure out what do we have to understand about complexity. So after this very general and hand-waving words, let me get to the specific thing. So the important thing is not to yak about systems in general. The important thing is to concentrate on one organism, one machine, and for years get at it from different angles, beat it to death, really understand what's going on. So I decided to talk about physics of Mitotic Spindle. So I could talk in principle about cell migration or some other biological machines, but I figured it's better to just concentrate on one of them and look at many different models, see what physics can contribute to study this thing. So Mitotic Spindle. One thing I have to tell in advance, when I lecture on these things to biologists, I talk about not just any mitotic spindle, but about the spindle in very specific organism, because in different organisms, like in yeast and Drosophila, there are important differences between the spindles. But for this audience, it's not very important, so I will sort of jump from one spindle to another without really telling you explicitly which spindle I'm talking about, because the physics of all of them is very similar.
Can you tell us what a mitotic spindle is for those physicists' background?
So in the next slide, I'll get to it in great detail. You just, more biologically minded of you should just keep in mind that I'm meeting incredible amount of biological details, which I can talk about for hours, so those of you who are interested in can approach me sometime. So I'll describe in greater detail what spindle is in the next few slides, but I just wanted to show in this introductory slide, this is not a artistic rendering, this is actual micrograph from microscope. So it's from a group of Kodrikov, who is in upstate New York, and it shows this incredible, spectacular thing when you have the focal points called centrosomes. You have linear biological polymers called microtubules sticking out of this focal point, creating what is called microtubule asters. Boundary of the cell covered with actin, another very important protein in the cell, and chromosomes in the middle. But let me actually, it doesn't work, right? Yeah. Oh, it does work. Okay, thanks. Okay, so let me tell you what the spindle is and what is mitosis. So memorizing the sequence of mitosis is a must for any biological student, and it gives lots of pre-med students nightmares because they have to remember every little detail and rattle them out at the exam. So it takes a while to remember it. Fortunately, you don't have to remember, because after I get over the slide, we'll be concentrating on specific stages and talking about small parts of this process. So in general, so you all know about cell division, right? When cell matures, it decides that it's time to produce two daughter cells from one mother cell. It divides. Before it physically divides, it has to perform a very important task. It has to duplicate genetic material and send equal copies to each of the daughter cells. So mitosis, in short, is this process before physical division of sending genetic material, copies of genetic materials to two daughter cells. Okay? So I'm not going even to mention the tremendous genetic and biochemical regulation networks which are making decisions when to go into mitosis, when to go into cell division. Basically, I'm not going to talk about cell cycle, which is extremely exciting area, that became quantitative actually decades before mitosis became quantitative. So those of you who get interested in cell cycle, it's even bigger area than mitosis. So mitosis is basically kind of physical part of this process. So it all starts in the stage called interphase. You have a nucleus, you have your DNA there, in the nucleus in a sort of thread-like fashion. And when the cell decides that it's time to go into mitosis, before that there's only one centrosome. So centrosome is kind of mysterious organelle. It has two centrioles and pericentriolar material. It's all basically kind of physical meshwork of proteins. The structure of these proteins is known, but it's not quite clear what's the function of this structure and what's going on there. The important thing for us is that centrosome is basically like a focus and anchoring point for microtubules, which are linear polymers, and we'll talk about them at length after this slide because those are the main players in this whole process. So once a centrosome becomes two, so it duplicates. And so you have these two microtubule asters, two focal points from which microtubules grow like rays from the sun. And then the cell goes into prophase. In the prophase, what's happening is centrosomes start separating around the nucleus. So they start at the north pole of the nucleus. They want to get to the equator at the opposite side of the nucleus. Then prometaphase starts. In the prometaphase, what's happening, nuclear envelope get broken. This is called nuclear envelope breakdown. At the same time, genetic material condenses into chromosomes. Right? So chromosomes are kind of, crudely speaking, of like sausages. And this condensation into, I see smiles, probably people remember the feast yesterday. If I knew better, I would skip the sausage because after that it was much more tasty. But anyway, so those are like sausages at this feast yesterday. And so condensation of genetic material into a chromosome, again, by itself is a huge area of biology with very interesting experiment and modeling going on, which I'm not going to mention. So chromosomes consist of so-called two sister chromatids. So those are kind of two sausages glued together. Each contains a copy, identical copy of genetic material. So one sister will go to one daughter cell in the end, another sister will go to another. But so far, in the prometaphase, there's kind of this droplet of glue. Oops. There's this droplet of glue between these sisters. So they are like Siamese twins. They are bound together. Besides all that, microtubules, these linear polymers, they start growing and shrinking, and you'll see that why they do it, because they hunt for the chromosomes. So in the end, they get all the chromosomes, and then when all the chromosomes are captured, the cell goes into the next stage called metaphase. At which stage chromosomes, which were initially scattered all around the nucleus, they get perfectly aligned at the equator between the cells. It's similar to when you have a race, you take all the sportsmen and align them at the starting stage. They have to start running at the same time. So that's why the cell does it. It aligns all the chromosomes at the equator. So you have two poles at which there are centrosomes in the poles. Equator with aligned chromosomes, and now everything is ready for actual physical segregation of the chromosomes. So then the cell goes into the first part of next stage called anaphase, first part called anaphase A, at which the glue between the sister chromatids is dissolved. So this sister sausages, sister chromosomes get sort of disjoint from each other. And at the same time, there's a those microtubules are becoming like springs. Each of them starts to pull the chromosome to which it attaches to the pole. So, and as soon as the glue is dissolved, the sister chromatids are dragged to respective poles. And then the problem is that the poles are too close to each other still. So it's dangerous because when there are lots of mistakes in physical division of the cell, which is called there's lots of mistakes in physical division of the cell. So if you have the sisters still too close, and let's say the cell starts to divide somewhere here, right? It could be a lot of grief. So the cell after this first stage tries to separate the spindle poles. So the spindle poles now get separated. In the end, the sister chromatids are separated from each other by great distance. And then the cell goes into the last stage called telophase, in which tiny nuclei are reforming around each set of the sisters. The sisters dissolve into genetic material again, and then physical process of division starts. The cell divides right here. But that's sort of the beginning of the whole other stage. So this process called mitosis, it's actually a big part of cell biology. It's sort of in terms of the amount of research which is done, it's I would say 10-15% of all research in cell biology is going about this. And of course, the traditional biological research always attacks really tiny part of it. For example, like any characteristic established lab, which is getting NIH funding amounting to $1 million for 2-3 years, works for 20-30 years, basically a lifetime of principal investigator to uncover all the details about 1 out of, let's say, 10 molecules which control this glue between sister chromatids. And there are hundreds of these parts, so you can imagine how much work and time goes into uncovering this whole detail. But what people starting to realize these days, let me get to the, let me stay with this slide for a while. So what people are starting to realize is this. So traditional biological research is basically about getting an inventory of all the molecules involved, plus figuring out the rates of